This is lesson 5, which is going to be our second example using VHDL. We'll do the example of multiple input gates. Now recall the definition of a multiple input AND gate. Remember, the output is high only if all inputs are high. And in VHDL we write Z is X1 and X2 and so forth. An OR gate, the output is low only if all inputs are low. And we write this as Z is X1 or X2 or up to Xn. Remember, a NAND gate is low only if all inputs are high. And we'll write NOT and then parentheses X1 and X2. So it's a NOT AND. The NOR gate is high only if all inputs are low. We'll write this as NOT X1 or X2 or. Just a NOT OR. An exclusive OR gate is high only if the number of high inputs is odd. And again, we'll write X1 XOR, X2 XOR, up to Xn. And finally, XNOR, the output is going to be high only if the number of high inputs is even. And again, in VHDL, we'll write X1, XNOR, X2, and so forth. So let's write a VHDL program for this. Here's the entire VHDL program. This is the entity, and this is the architecture. Note that the input X we're going to write as a standard logic vector 4 down to 1, and Z will have 6 down to 1. Then in the architecture we'll just write the logic equations. X6, Z6 is going to be the AND gate. Just AND them all together. Z5 will be the NAND gate, not AND. Z4 will be the OR gate, OR them all together. Z3 is the NOR gate, not OR. Z2 is the exclusive OR gate, 4 inputs again, and Z1 is the 4 input XNOR gate. So that's all there is to it. Just write the 6 logic equations in terms of the inputs X and giving the outputs Z. Now we'll need a top-level design so that we can implement it on our FPGA, on our Nexus 2 board, for example. So here we'll use the switches, 4 inputs, switch 3 down to 0 for the inputs, and we'll use the rightmost 6 LEDs, 5 down to 0 for the outputs. Then the architecture of the top-level design. Remember, between architecture and begin, we list the component, gates 4. That was our entity name for the 4 input gates. These are the inputs, X4 down to 1, Z6 down to 1. And then we'll use this port map statement to connect the X, that is this 4 down to 1, to the switches, which remember were 3 down to 0. As long as the number on each side matches, we can set the 4 down to 1 equal to the 3 down to 0. So the X4 goes to switch 3, and so forth. Same for Z, just set Z, connect it to the LEDs, LD 5 down to 0, 0. That's this Z 6 down to 1. Now if we simulate it using our all-deck simulator, we see that sure enough it works. Here's the AND gate, which is high only if all inputs are high. NAND gate is just the opposite of the AND. The OR gate is low only if all inputs are low, and it is 1 otherwise. And the NOR gate is just the not OR. The exclusive OR, notice that the inputs are 1 only if we have an odd number of 1s. For example, here we have 1, 2, 3 1s. You see, and over here, here we have 1, 2, 3 again. The first one here we just have 1, 1. In XNOR, is just the opposite of the XOR. This will be 1 when the number of ones is even. Number of inputs are even. Okay, that's it. You can go ahead and download this to your FPGA and see if it works on your board.